All right, so I'll just write in here until I run out of space. The first feature, so I'm going to do the 5 features of the distribution. The first feature is a measure of center. In other words, the expected value. So you want to be able to say, what do we expect the next person coming to the store to spend? How do you think we'll figure that out? No, not center. Center is 2. Sorry, I messed that up. I'm going to move that. First, we have to do center is the second. Before we get to the center, which is critical and everybody wants to know about it, we have to do one thing first, and that is discuss the shape. What is the shape of the distribution? What are the options, right? So either the distribution is symmetric. Symmetric looks like a mirror in the middle would reflect the same on each side. Okay, that's symmetric. Our distribution is non-symmetric, or we say, in this case, right skewed. All right. So what is that? There's a tail on it. In other words, there's a few high values that are away from the majority of values over here. When there's a few high values or values on the right of a number line, then it's called right skewed. The skew identifies the tail, or where there's a few. Okay. So I'm going to put that down. The shape is right skewed. Now, depending on the shape, we will know which of the measures of center that we should use. Now, there's several measures of center. The most popular are mean, or the average, median, and mode. Does anybody know the difference? Have you heard these terms before? So here we have a symmetric distribution, a right skewed distribution with a few observations higher than the majority of data. And here we have a left skewed distribution. Some examples of a symmetric distribution. Do you know of some examples? When will you see a symmetric? So what is a symmetric distribution? It's where most of the data are around or close to the most frequent observations. And then there's a few high values and then just as many lower values. And then there's even less, much higher values and just as many much lower values. And it just spreads out like this, balancing over some expected value here. So an example of symmetric data would be height or weight of adults. And like, so it's very regular, very, nothing very strange, right? Because and just as many people that are really tall, there's just as many people that are like much smaller than the average. Another example of symmetric data are standardized test results like the SAT or College Board. And in fact, a lot of the statistics that we do, and even in this course, we like symmetric data. And a lot of the results, or a lot of the developed statistical tools work with symmetric results. And after this unit, we're going to focus a lot more on symmetric results. So you need to know the difference between symmetric and skewed. What's some examples of right skewed data? We saw in the grocery store, that was one example where most people spent between, $2 and $30. And then a few people spent almost $70. So also similarly, income is right skewed. You know how they talk about the 99% and the 1%. Here you have the 1% earning much higher income than most people, most all people. And what's an example of left skewed? So here you have the variable with just a few small values and most people are high or relatively high. So my example that I use is school grade completed. If you take 18-year-olds, most 18-year-olds will have finished high school, right? Or grade school. Some of them will even go beyond, or like most of them will be almost finished. So at least the most of them will have grade 10. And then you have some that have all of it, still very high amount that have all of it. And then you have people who have less, and you have a very few people who have no grade school education, who can be maybe disabled or mentally challenged to have started or completed grade school. So that's my example. So knowing the story of these shapes, we're now going to talk about what is a measure of expected value. In this case, the mode, median, and mean are all the same. So what is the mode? Mode is the class. Remember, when I smooth out, notice I don't have any of the data showing here. This is a smoothed out distribution. And the observations in here are the most common, right? This is the highest peak. This has the most. In other words, it's the modal class, the modal class. That's the word for the most. Where is the modal class over here? In the right skewed distribution. A, B, or C, which one has the most observations? Which one is the tallest? A. A, right. So A is the modal class here. And what is the modal class over here?
C.
C. Okay, so that's modal class. You can see it. That's why it's popular. Okay, that's why it's popular. And that's not the only measure of center, though. So the other one I told you about was the average, right? We begin with the symmetric distribution, and I told you the modal class will be the same place where we find the mean and the same place where we find the median. The mean is just the average of all of the values. I add up all the numbers and I divide by how many there are. So this is going to use all the values in the calculation, right? When you have skew distribution, the mean is not the modal class. It's either B or C. And here, A or B. The other one is called the median. The median is the median is a percentile. It's known as the 50th percentile. It's where 50%, half of the values, lie to the left of it. So it's more focused on the position of the values, not so much on the number itself. Like we want to find the number, but we're more interested in its relative rank. It's the order and its relative rank. So for instance, okay, once you finish writing, I'm going to show you with the data that we have, the difference between the mean and median, and then we'll come back here. So here's the data. Where is the middle of the data? Which is the middle observation? Which is the observation that divides the data in half? We have 25 observations here and 25 observations here. So which is the middle observation? Is there a middle observation? So you feel uncertain, right? Because there are two middle observations here and here. What we have to do for the median when there is not an exact middle is you have to average of the two middle observations. So in this example, the median is equal to 20.58 plus 20.89 divided by 2. What is it?
2074.
Okay, so you just added them and divided by 2, right? So you just
Yes.
went 20.58 plus 20.89 equals divided by 2, 20.735. Okay, so what I'm going to do in this class is my rule most of the time to get the same numbers as me is to keep 2 more decimals than the result of, or sorry, 2 more decimals than the data that you used. Here we used 2 decimal data, so I have to use up to 4 decimal places, if you understand what I'm saying. 0.735. So what I have to do is write, but because this is dollars, dollars don't exist in more than cents, right? So I'm going to round. Okay, so it says it in the notes that my rule is to keep, in general, keep 2 more decimals than original data. So that is the median. Notice I only averaged these 2 numbers. I didn't average any of the other numbers. The way I used the other numbers was to create like a buffer around them. I just wanted to go in the middle, and the other ones are just showing me where the middle is. All right. So in other words, I never use this number. That's very different. Look, it's 3 times that. It's more than 3 times. So that would affect my calculations. In fact, let's calculate the average. Okay, so this is going to be a lot of work though, right? How did I do this? And I think, well, in this problem, I'm going to just tell you, because I don't think I ever did that. I have it calculated somewhere, but in this problem, because the data are skewed, we don't use the mean, all right? We actually refer to the median as the center, because if you do the mean calculation actually comes out to a much higher number. I'm just going to write that. Do you know why? You can prove it to yourself, but do you know why? Because the mean, I would have to add all these together and divide by 50. When I do that, these higher numbers get averaged in, and the mean will be much, much higher. It's a lot to punch in. I must have that number somewhere. Thinking if I even calculate that. So, all right, we're going to do the mean on another problem, not this one. So when the data are skewed, we use the median as a measure of the center or the expected value, and our median is equal to 20 or approximately equal to $20.74. And we note when data are skewed. So data is a plural, so I have to say are, not is. When data are skewed or the distribution is skewed, we take the median, we use the median. There's another document. Let me check if I put it in there. Yeah, I don't think I calculate the mean anywhere. But okay, trust me on that one. And I'll show you another example. I'll prove it to you. Okay. All right. So that's number 2. So let's go back here and summarize what I'm saying. It turns out that because the median only uses those central values and 2 of them, it's not affected by the few very extreme values. The very extreme values will pull the mean towards it. So when looking at this, which one of these is the mean and which is the median? So which is the mean, B or C? So the C is the mean. And over here, which one is the mean, A or B? Which one will be the average? I don't have the exact numbers. It just will always be the case that A will be closer to the tail than the median. And the median is the compromise between the mean and the mode, right? It's more of a central value because this one gets a little bit pulled away. And same thing here. So the median is always the compromise in between. So, yeah. So the median, this is the mean class, or the mean is found in that class. And the median is found in here. Any questions? So when data are skewed, you use the median. When data are symmetric, it doesn't matter because the mean, the median, and the mode are all the same. The convention, though, seems to be to use the mean. People use the average. That's the one you hear about all the time. But you'll notice, you should start noticing if you hear news reports about income, they'll always say median income. Maybe you don't notice it right now, but you should begin to hear that. They don't talk about the average income. They talk about median income because they're accounting for the fact that the mean income will be more distorted and too, really far. So why do we care? We care because the goal of statistics is to make predictions, right? Or to know what to expect. So you need to get the right expected value. The better of the three is the median where the data are skewed. Not the mode, even though you can see that, that's not popular as an expected value, okay? When the data are skewed. Okay, so the next thing we need, when you hear reports, you have to make a report about a distribution. There's a lot of numbers there and there's a shape there, and we want to reflect that. So we tell or we report that it's a right skew distribution with an expected value of $20.74, despite the fact that it's very far away from, 3 times lower than the extreme values. And we're going to talk about that later too. The third thing we want to talk about is the range or the spread of the distribution. The spread, you can begin by talking about the range. The range, you could say, is the maximum value minus the minimum value. And you can even report the maximum of the minimum of $2.32 up to a maximum of $69.49. And you can subtract them so you can show how long the range is. What is the maximum minus the minimum?
$67.17.
Very broad, right? $67.17 range. I keep the units. And notice I'm keeping the decimals in my report. Even though I discarded the decimals in the graph, I keep the decimals in my report. You need to go back to the original data to make report. So we have the median, we have the center and we have the spread. When the data are skewed, there's another measure of spread that we like to use, and that is called the 5-number summary. Now you already have we have 3 of the 5 numbers because we got to put minimum. You have to put Q1, Q2, Q3, and the maximum. Q stands for quartiles. So these are percentiles of 25% each. They're marking the value to which 25% of the observations are below, 50% of the observations are below, 75% of the observations are below. We're going to go back to the numbers above, and you're going to tell me, well, let's put in what we have so far. We have the minimum. We can put that down, 232. We don't know Q1. We got to calculate it. We do know Q2. Q2 is the second quartile. 2 times 25 is 50%. Okay. So it's really the median. And the median we got was 2074. That's the median. And then Q3 and then the maximum. All right, so we only have to find two, the first quarter and the third quarter. The data are separated into 50% of the data below the median and 50% of the data above the median. What we need to find is the 25th percentile. In other words, the middle of the first half, and then for the Q3, the third quartile, we need the middle of the second half. So how will you find the middle of these? The rule is for finding the median, which I didn't show you here, but it's going to make good sense. The median is found at the n plus 1 over 2th observation. So you take the n, you add 1, and you divide by 2. For this problem, you would take 50 plus 1 divided by 2, which was 25 and a half. And when you get a half, you have to go between or average the two values that are around it. So now let's do this. Where's the median of this data? In this case, half of the data, n is 25. So the median is at the n plus 1 over 2, which is 26 over 2, which is 13. 13 observation is here. This is Q1. And it looks like the half. You can see it. It's halfway. But this is the rule to finding it. And then right over here, it's going to be 38. You have to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this will be Q3. So the rule, this is what we use to find the median of the first half. And here n was 25. Also in here n was 25. So this is going to be Q3. So 25% of observations are below it. Q3 is the third quartile, 75% of the observations are below. How do I know it's 25 and 75? Because this whole thing was 50% and I divided it in two. How do I know it's 75? Because half of 50% is 25%, and this is 50, so 50 plus 25 is 75. Am I going too fast? Or are you guys good?
I'm good.
Yeah, you're good? Okay, good. So now we're going to transfer these numbers, 1435 and 3380. Oops. That separates my data. I lost some things there. So you're going to tell me the numbers because I'm not going to remember. 14.35 and And what was the other one? What's Q3?
33.8.
All right, so that is the 5-number summary. Now, what do we do with this 5-number summary? We're going to learn more about that in this unit. But for now, I guess that's what it is. In addition to making the range of values, from here we calculate the what's called the interquartile range. The IQR is known as the interquartile range. And it is calculated as Q3 minus Q1. How many observations are between Q3 and Q1? Anybody know? What percentage of observations between? So if you have a position where 25% are below, and then you have a position where 75% are below, how much in between them? 75 minus 25 is how much? We find 50% of the data. I mean, not a majority, but half the data. So we're interested in the interquartile range because it's in the range. It's like the more stable part of the distribution in the sense that, not stable, but it's not in the extremes, right? It's not the extreme values. It's where it's more regular. So we want to see what is the pattern of the data. Like, if you have a group of people that are all like the physicians, you could have some physicians that make a lot of money. Radiologists make a lot of money because they run clinics and they make a cut on every, not clinics, laboratories. And so they make a lot of money running laboratories. So those physicians make millions of dollars, and there's other physicians who are family practitioners with a 9 to 5, and they don't make as much, $200,000, $300,000, right? So you have a range. But the radiologists are kind of extreme. So we want to look more in the middle. So we're going to look at the middle 50%, right in the middle, and see how spread out they are. And that's going to give us a measure of regularity among physicians' salaries. Okay, sorry about that. All right, so that's what we report. So those are all the details for spread. We say the range, calculated range. We put the minimum to the maximum. We make the 5-number summary, and we calculate the IQR. Oh, we need to get it. So yeah, get the IQR for me. Okay. So did you get it? Q3 minus Q1?
$24.45.
24.45?
Yes.
Okay. Any disputes? So this information says that the middle 50% of data has a range of 24.45, but then if you think about it, are you sure it's 24.45? I just got a different number.
19.45.
$19.45. Do you see what you did wrong, Lucero? Lucero?
Yes, I see you, but
Okay.
I did wrong.
Okay. Okay, so so the median is 20 something, 20.74. The middle 50 is 20, but yet the at the beginning it's like there's from the middle to the minimum value are 20, but then from the middle to the extreme value is 60. So it just, by looking at this 5-number summary, you can tell that the data are skewed. You don't even need the graph, okay? So often people just calculate the statistics and don't even make the graphs. But the problem with that is that you need to know how to analyze the statistics. You first have to know the shape. The 5-number summary will tell you the shape, because you'll see between here and here is 19, but there's very different between Q3 and and the maximum. There's almost 40 between there, but between here, there's only how much? Like 12, right? So this shows you that there's a right skew. And I explain that in the videos as well. You can see, or we'll get to the point, we'll talk about that. Okay, so you can use the IQR to see the graph, basically. What you don't see in the IQR are, not the IQR, the 5-number summary. You don't see the peaks of the data, okay? You don't see that part of the graph. So that's what you need the graph for. But you do see if it's skewed or not. But you don't get to see, all this going on. All right, so we've done shape, center, spread. And now okay, I'm sorry. I have to take just a minute break, okay? I'm working on submitting a paper. Okay, let me have 5 minutes. I'll be back in 5 minutes, okay? I'll be right back. Okay, I'm back. What were we doing? We were discussing the IQR. All right, so we did the 3 features. The 4th, we're going to use this 5-number summary to verify if we have what is called a statistical outlier. So what we're going to do is call that. So this was 1. Sorry. 1. 2. 3. And now we're going to do 4. It's called gaps and outliers. All of this is nicely typed up in the notes, so don't worry too much that you either wrote it wrong. You can check the notes to verify. I'll show you where that is. Okay, gaps and outliers. Are there any gaps in the data? Do you see any gaps in the data? There's 1 gap here, you see? There's no data for this class. Can you tell me which class this is?
Five.
Not 5. 55 to 59. Right? So there's a gap. You can write 55 to 59 like that. No data. There's no data there. It's not bad. It's nothing like that. It's just a hint that, oops. It just hints that these values are different, set away from the rest of the values. And that's what we want to establish, okay? So our goal is to find the general pattern of the data and report on that, but also report on data that's significantly different. And the way we are identifying just in statistical terms, we have a rule to find statistical outliers. Statistical outliers are found I'll explain more in a bit. So statistical outliers are found where they fall outside of the general pattern of the data. And the way we're going to work with that, I'll put the rule here. Let me I'm going to get my drawing from here because I have a really good drawing I'm going to steal from here in the notes. This one, right? So this is the 5-number summary laid out in a graph that's known as a box plot. So I have here the minimum, the maximum, the Q1, the Q3, and the Q2. You see that? I've calculated the IQR and it makes a box. And it shows you what I was talking about, that the 50% sits in the middle. It's, not too far off is the minimum, but the maximum is really far away. The rule is if the maximum or any values are beyond 1.5 of these boxes, then it's considered a statistical outlier. So what we have to do is take the measure here of this box, and we calculated it already, right? It was 1945. And we take the measure of that box and we put it 1. Let's do it. 1, and you have to go in a half more. So let me take half the box. Every value that's beyond 1.5 of the boxes is considered an outlier. It's too far. It's too strange. And statisticians figured out that that's good enough to say it's warrants investigation. What's going on? Why are there these extreme values? Because maybe there was a recording error, or maybe maybe something really interesting has happened. So you're identifying something that's outside of the regular pattern. So the way that you do this is you take, on the side where you see the skew, you take 1.5 times the IQR and you add it to the end of the box where you're checking. The end of the box that I'm checking is 3380. Or in this case, I'm going to say Q3. So that's if this is where the long arm or whisker, it's called like the cat whisker, the whisker, or the mustache. That's where the mustache is very long, or the whisker is very long. So when you calculate that, you get that it ends here. So it's a little longer. I guess I drew it a little longer than I did here, but. So this is 1.5 IQRs plus 3850 brings me all the way to here. $62,975. So any values beyond 62,975, I'm going to call them outliers. So we got to go back to the data and check which values are bigger than 6297. So which ones are bigger than 6297? These 3. Okay, so observation 6385 is in there, 6430, and 6949. So I can mark them. There's like this one, and they're in there somewhere. 385. I'm not doing a great job, but they're in there. All right, and those are known as statistical outliers. So you can mention them by number. 6385, 6430, and 69.49. So all I've done so far is just extract all the data. And in the end, we're going to answer the questions. Okay, so you should be able to draw that and make that interpretation. Another thing you can see with the box plot, as I explained before, that you can use the IQR to check for skewness. And I have a video on it, but I'll just give you a brief explanation. First, you're going to compare these two inside the box. And you see this one is a little longer than this one. It's not massive, but it looks a little bit longer. And you would say that the inside is right skewed. It's not a great color. And then comparing on the outside, you compare this part of the whisker with this part of the whisker. The right is again much longer. Notice that even though there's 25% of the observations here, there's also 25% of the observations here. These ones are much more spread out, all right? Because we've divided the data into groups of 25%. So if there were 100, there would be 25 in here, 25 in here, 25 in here, and 25 in here. We don't have 100. We have 50. So it's it's a quarter of 50, which is like, half of 25. This is 12. It's like 12 in here, 12 in here, 12 in here, and 12 in here. That's what we've done. And since you see that the inside is right skewed and the outside looks right skewed, without seeing the graph, let's say, you can conclude from the box plot that the data are right skewed because they're reinforcing each other. So first you go inside and then you go look outside. Any questions? You spent the whole class on this problem, but it's worth it to get you started. So there are 5 features. The last one, this was the 4th that we just did. The 5th is to talk about peaks. You need to identify the class where the peaks are. So what class has the peaks? Sorry. Here is, if I'm going to go with the yellow that I said, I should clean off the blue, right? I cleaned it too well. So where are the peaks? Tell me the classes where the peaks occur for each modal. So there are 3 peaks, right? There are 3. But to identify the peaks, you got to tell me the modal class of the peak. So in other words, the highest point or the highest class. This one is the first one is between 15 and 19. The second one is between 30 and 34. And the last one is between 60 and 64. I'm going to say within each peak. Any questions? So when we started, Claudia asked me, why am I going by 5? What is the justification? And now, oops, I'm going to explain that. This is the full answer. But this was our written work, right? You can find the answer in the document called sample problems. So let me show you that. This is the document called sample problems, and it lists 4 different sets of problems. I skipped this one. This one's in the notes. This is the one that we did, spending data. This is another one that I discuss, and the hot dog data. All the data are here. And I go through the graphical representation of each. Okay, so then I do the summaries. So here are the summaries. That's the first one. The one that we did was the second. So it's here, you see? Shape, center, spread, phi number summary, median, Q1, Q3. I explain everything. And I make a note here to be sure to make these calculations by hand, since statistical data, like this software too, the calculations in statistical data are different from doing it the way that I showed you with the n+1/2. It doesn't make it wrong. It's just one thing that never was standardized, it seems, in statistics. The numbers are very similar, but don't get thrown off that they're slightly different. If you have any confusion, you can let me know, but I'm not going to show you statistical data for phi number summary. So we're just going to do it the way I showed you. It's more intuitive. Well, the other one's not bad either, but I'll talk about that in the notes as well. There are the calculations of gaps and outliers. And here are the, oh, I didn't put the dollar signs on, which I could put, because it's all about dollars and cents. So you can add all of that to your notes. And the conclusion, the center of the distribution is at the median of about $21. I'm just rounding it. So $20.74 is like $21. But 10% of the customers spent over $50. The shape revealed by the stem plot, therefore, is of interest to the store management. If the big spenders can be studied in more detail, steps to attract them may be profitable. And I explain here in the peaks that in the first mode, because this is like trimodal, right? There's 3 modes. The smaller one where, and then the second one where people spend more money, and then the few people that spend quite a bit of money are in the third class. Or the third, not third class, the third peak. And then you can go on to explain if you think it's income related or it's different kinds of customers that are coming into the store. Maybe there's a school nearby and some kids drop in after school to grab a drink. And that's why they're spending, $5 or $10. Then there's the grocery shoppers in the middle. And then there's these people who are coming in and buying, some extra supplies for their restaurant. So that's to be determined. Who are the low spenders and who are the middle spenders and who are the high spenders? All right. So additional comments are, look at the stem and leaf. If I only went by 10, so here I make the stem and leaf going by 10 as opposed to going by 5. And what do you see is different? Would you say the shape is different? Is it still, it's still skewed to the right? Do you think it looks more symmetric? In fact, it's still, okay, so if we went through all the 5 features, the shape is still skewed looking because this would be the center and then these are kind of outside. The calculations that we made would still be the same. The center, we would still use the median. The spread, we would use the 5-number summary. The gaps and outliers, we do the same. The difference is the peaks, the 5th feature. This only shows 2 peaks. It hides the middle peak. So because of that, and because I think we're just clumping too much data together, I want to spread it out like this and show the second peak in the middle. All right, so that's why I chose this one, going by 5 as opposed to going by 10. How do you know what's the right thing to do? Make a few different graphs and see if they conflict. If they conflict, you really have to make a decision. If they don't conflict and the 5 features are the same for all of them, it doesn't really matter which one you use. Okay, so that's the 5, that's my introduction to this unit where you do a lot of calculations. And I teach you how to use your calculator to make them. All right. Let me talk a little bit about the mean, a little bit more about the mean. You see, I would let you guys go if I knew you do your homework, but you guys proved to me you didn't do your homework last week. So that's why I'm trying to help you out, move you along. I prefer if you guys did the stuff I told you and then we just have a short meeting, but I'm intent on keeping you guys on schedule. All right, so I want to share my iPad. So talking about the mean, the median, and the mode you can see, the median is the compromise between the mean and the mode. What is the deal with the mean? The mean is actually, because you use all the values to compute it, this is the symbol for the mean. You add all the values and divide by how many there are. This is actually known as the center of gravity of the distribution. It is the value it's the value that is closest to all the other observations. It balances, therefore, the distribution because the weight on either side is perfectly balanced by that value. The mean might not be one of the values. It's the average of all of the values. So notice if if the distribution is skewed, to actually balance the distribution where the density, like this area, is the same as this area, it forces the mean to be drawn towards the tail to make it balance. Okay, so if you try to balance a skewed distribution at the mode, it'll tip over, it won't work. If you try to balance the distribution over here, clearly this is going to tip over. There's much more weight over here. Okay, so it's somewhere between, in between those two. It's not at the mode, and it's not too far out, but it's pulled enough beyond the median will always be in between this and this. It'll be over here somewhere. Okay, so that's what's going on with the mean, and that's always because all the values go into its calculation. Okay, so the median was the middle observation or the 50th percentile, right? We found the position of the two middle observations and had to average them to actually find the value of the median, where 50% of the ordered observations on the left and 50% are on the right. I concluded that if the data are symmetric, you use the mean, that's the convention. Even though the mean, median, and mode are all in the same class, we measure the mean as the center. And if the data are skewed, we use the median instead because it's not sensitive to those few extreme values that make that tail. There's a fourth measure of the center of a distribution that I introduced here. And there's other measures, but these are the ones that you'll see in business or in finance. One is the geometric mean. Geometric mean is calculated by taking all the values, multiplying them, and then taking their root. This is used a lot for interest or growth rates. And it also is like the median, actually, it's not sensitive to extreme values. So the geometric average is found as with rates. If you want to find out, let's say you have an investment, and every period it grows, the investment grows at an interest rate that varies, or a rate of growth that varies. You can figure out the average of that growth over that period by multiplying these accumulation factors together and taking the square root. I won't do this in this course, but you might have seen that, or you might see that sometime. It's just another measure of average when you're dealing with rates. So don't worry, you won't see that if that worries you. Then we talked about the spread, and we talked about the different measures of spread. So here we have . I have here two symmetric distributions. So let's say we have these two symmetric distributions. In a symmetric distribution, we'll learn that we use the mean, because we learned that, right? And the symbol for mean is like X bar. Okay, wait. So if a distribution is symmetric, my short form notation for distribution is like this. For symmetric distribution, we calculate X bar as the mean or the center of gravity or the center of the distribution. And we use S, which is called the standard deviation, as a measure of spread. I want to take some time to talk about symmetric distributions and the standard deviation, I think, before we go. So we're going to talk about what that is, but it's a measure of how spread out the data are if the data are symmetric, okay? So this one, so when I smooth out the distribution, remember what am I saying? I'm saying that if I had all of the data, if I had more data, I believe it would follow this pattern, okay? What I'm saying is that that would be the mean, and that would be the mean of that one. Let's say they had the same mean, okay? Let's say they were the same. Mean star, mean star. Let's say this represented you invested in a company, and this shows you the this is data on your returns. So like the percentage of return that people made over a significant time period while holding that stock. So this is the same mean, but this is stock 1 or stock A, and this is stock B. Which one of these, if the mean is the same, which one of these are more less volatile or more reliable or more predictable? I didn't put any numbers in there. Just assume there's enough numbers in both of them to make this drawing, and this represents the maximum data I could get on these stock. Which one is more like or less risky? Which one is less risky? More predictable, more reliable? Think I need to put numbers there? So let's say you go to the computer and you see that you got on Monday, you got the average return. So you got the number right here. Then on Tuesday, you like right about here, you got this return. It's really good. But then on Wednesday, it went down here. Okay, so it's a little bit lower than the average. So it's kind of all around here, right? It's very tight. But in here, let's say, the same percentage that is in here. So what's the percentage of data on this side? What percentage of the information or observations are on the left, if this is the mean?
50.
Yes, very good. So it's 50% here, 50% here. Let's do the same thing over here. So what percentage of observations are below here? The same, right? 50%.
Mm-hmm.
So that means that you have a chance, just the same chance, but only going this far away from the mean. But look here, you could go this low. This is more risky. It's more spread out. Okay, you could get this high, which is much higher than here, but you can make a loss. You can get, very low with 50% chance. You can end up, somewhere in here. It's all spread out. So this one is the tighter, less volatile, more reliable, less risky investment than this one that's more volatile, more spread out. So in the more spread out one, S is larger here, okay? The standard deviation calculation would be larger here because it's more spread out. So we're going to look at the standard deviation and the interpretation of the standard deviation before we go today. So S is larger in B than in A. I also introduce a concept of percentiles that are different. Like we talked about the 5-number summary. The Q1 was the 25th percentile, Q2 was 50th, Q3 was the 75th, but I can make other percentiles. I could say I'm interested in the top 10 percentile, right? That would make me interested in the top, like the top 10% of students. So if I'm interested in that, I'm going to show you on the notes, I explain how you make that calculation, given your data, how you find the pth percentile, in other words. So for the range, for the spread, I introduced the idea of the range, the standard deviation now we're going to talk about, and the 5-number summary. There's another measure for spread, and that's known as the coefficient of variation. And I'm not going to use that much in this course, but it's a way to look at, and a good way to explain this is to look at the finance graphs again, the charts or the distributions. Standard deviation is like a measure of risk or volatility, right? And the average is the expected return. So you can take your risk and you can spread it out over your expected return. This is like your benefit and this is your cost. And it gives you an idea of how like it weighs down the riskiness. So you can look at, well, for such a benefit, is this risk worth it? In other words. And it gives you an idea if relative to the benefit, is that risk really substantial? Okay. So we're not going to do that in this class, but that's how it works. Should I give you an example, or are you guys okay if I continue? Because we won't use this in this class. I just wanted to put it in here because it comes up in it does come up in financial data. So I use some of this language when I talk about the 5-number summary versus the standard deviation. And I say the 5-number summary, like the median, is resistant to outliers. It's not affected by extreme values because they don't even go into the calculations of the Q1, Q2, and Q3. I don't use all the values like I do in the mean calculation. So when I did this example, I used the same mean here. I said this is the same as this one, and this one was more volatile, and it was easy to choose. But the coefficient of variation is useful when the means are not the same, when they're different, and they have different risk. They have a different level of risk, but also a different mean. So to put all the numbers together and be able to compare them, you do this. Okay, basically you scale or rescale the standard deviation by the average or the expected value. All right, so like I said, that's not going to be in this course, but I have to mention it there. Okay, so let's we talked about peaks, gaps, and outliers, and just a point about gaps and outliers. When you find an outlier, like I said, you need to investigate. Is this a data entry error? If it is, try and fix it. Is it a measurement error? Meaning there's something went wrong with your instruments when you were trying to measure, or you had a staff member that didn't know what they were doing and they measured things wrong. In that case, you might want to investigate and drop the observation because you don't want wrong data, right? You don't want errors in your data. But there could be something very significant and important happening, and you do want to leave that value in. So that investigation will turn that up too, all right? So maybe you don't want to drop. I had an engineer, I always have engineering students in this class, and one time a student told me that she just, in her where she works, they just dropped extreme values to make their calculations. And I say, are you sure? Like, you know what you guys are doing? I mean, I didn't say it like that, but they must have had a good reason to drop those data. They must have been sure it wasn't something significantly different that they were dropping it for. It was just like something, something different and interesting. They dropped it because they suspected it was just an error in the data. All right. And then we talk about peaks. This is a unimodal. This is a bimodal. And the one we saw in the exercise was trimodal. 3 peaks. All right, so what we're going to do next is this problem. I'm going to take the data with me to another page. Okay, so we're going to talk about the standard deviation. Now, the standard deviation should only be used if you suspect or you feel that the data is more or less symmetric. In other words, there's a center to the data and there's some values above it and some values below it. And there's just as few values farther above as there are further below. So it spreads out evenly from the center. So provided you're dealing with symmetric data, we assume here the data are symmetric. And what we're going to do is measure. Okay, I'm going to show you how to do this, like where the formula comes from. Okay, hold on just 1 second, okay? I have to check I have a meeting tomorrow. Let me check something. Hold on. a 2-minute break. Sorry. Okay, I'm back. Sorry. All right. So what we want to do is talk about this formula and use it to derive the standard deviation and interpret the standard deviation. But essentially, I'm going to show you how to do this using the calculator that you got. All right. But I really want you to understand what it is. We begin here with the mean. This is the formula for the mean. It says that you need to sum all the observations and then divide by the number of observations. So this is the symbol for the sample mean. The sample mean intends to estimate the population mean, which has the symbol like this. It's a Greek letter M for mu or mean. The sample standard deviation has this formula, and it estimates the population standard deviation. Whose symbol looks like this. And these are universal symbols. So if we had all the data, we could calculate the average of all the data. If we had all the data, we could calculate the standard deviation of all the data. But we don't have that. We just have a sample. As a consequence of not having the mu and instead using X bar in here, we have to compensate, and I'll get into that when we get to that point, okay? So what are we doing? We begin by calculating the sample mean. To get the sample mean out of our calculators, we first enter the data into the worksheet for statistics. We go to second data, and here we enter our values for X. And so we use the symbol X because that's just a standard for observations. And the subscript I tells you the first observation, the second observation, the third observation, the fourth and fifth observations. So this means observation 1, observation 2, and so on. So we're going to put this data in. We're going to put 2, enter, and scroll down. Now it says Y. I don't have a second set of data right now. We're going to work on that when we get into Unit 3. Right now, we just have one set of data. So I continue. I just scroll past that. I ignore that. Then I put in the second observation, 8. Enter and scroll down again. The third observation I put in is 10. Enter, scroll down. And then 16. Enter, scroll down. And 5. Enter, scroll down. Once I'm finished, I just review the numbers, 2, 8, 10, 16, and 5. So all the data is in there. And now I ask for the statistics. Second stat gives me the linear data or linear statistics. Scrolling down, N is 5. X bar is my answer here. It's $8.20. So this data actually represents spending pocket money of a student that was collected. It's a very small data set, just so for illustration purposes. So that's the mean. And if I scroll down one more time, I actually get the standard deviation. It has the symbol SX. In our class, I'm just going to use S. It uses SX because that's for the X variable, but for the Y variable, it'll have SY. So it's to distinguish them. So I'm just going to use S here. And S is $5.31. So I have the answer. Now, how do I find the answer using the formula? That's what we're going to talk about. And then we're going to interpret. I hope we have enough time. So what is the standard deviation? The standard deviation goes beyond calculating the average. It tries to get the average of the deviations from the mean to get a measure of how spread out the data are. So what is a deviation from the mean? A deviation from the mean is this. This is a deviation from the mean for each observation. So you have to take the value here minus the mean. So $2 minus $8.20 is what? I'm going to put it there. So $2 minus $8.20 is negative $6.20. $8 minus $8.20 is negative 20 cents. $10 minus $8.20 is $1.80. Oh, I should put it lower. $16 minus $8.20 is $7.80. And $5 minus $8.20 is negative $3.20. So those are my deviations. Some are very small, because 8 is really close to that mean, and some are really far away, $7.80. Some are negative and some are positive. So why don't I just average the deviations from the mean? Can you guys try that without me? Put them in your calculator using the data key. Now I have some stuff there already, so I need to clear that up. The way I clear that is I hit second work, so I can start over. So if you put this in $6.20 with a negative, enter, and scroll down to X2, and you put 20 cents with a negative, and you scroll down to X3, and you put $1.80, and you scroll down to X4, $7.80, enter, and finally $3.20 negative. Do that and tell me what you get as the mean. If you didn't buy the calculator, I already mentioned you can get it on your iPad or your iPhone as a financial calculator or on Android as a financial calculator. It's free. The free one is not as straightforward as the $15 one. Sometimes there's some glitches that I don't really know and I can't help you with. Unless you ask me, but you won't know maybe until it's too late. You should be able to order the calculator on Amazon, eBay. Students found it for $10. If you really can't find one, you need one, I can hook you up with Student to sell you one. So keep me posted. So what do you get when you add those together? Guys are quiet. What is the average of these numbers? You can even, if you don't know how to do what I just showed you, you should ask me or just add them together. What do you get? Add them and divide by 5. Fabian, what do you get? Add them together and divide by 5. What do you get? Sergio,
I am adding them up.
okay.
I don't know if it's right, but it's 1.92.
Not right.
No?
I keep going. Obviously, this is important to do because you guys can't do it. So let's keep working on it till we get it. So did you use the did you use the calculator or just another calculator?
Okay, I got 3.84.
No.
Ah,
So if you want to add these, I put them in the data. Who has the calculator? Who bought the calculator? You guys are making your life more difficult if you don't buy the calculator. This is the easiest thing to do is get the calculator, and these calculations are very easy. I just got it in less than a minute. I got the answer already. Anyways, if I was going to add these up, it's $6.20 with a negative plus 0.2 negative plus 1.8 plus 7.8 minus 3.2. What do I get? 0. You get 0. Is that a coincidence I get 0? Then I divide by 5. 0 divided by 5 is? I'm going to put it in red. Okay. If you do the deviation from the means and you average them, you will get 0. Why will you get 0? Because the mean is the center of gravity. It is the position that's closest to all the points. It sits right in the middle of all the points, balancing the distribution. So the deviations on this side are balanced by the deviations on the other side. So if I'm getting the deviations from the mean on both sides and I add them, I'm going to get 0 every time. So I can't do that. I can't just get the average of the deviations from the mean, which would be very easy. Unfortunately, it's not going to be that easy. The problem is the negative signs. I don't really care if I'm above the mean or below the mean. What I care about is the magnitude of the difference from the mean each way. So I really just want to get rid of the sign and then divide by 5. So statisticians developed a whole bunch of statistics doing that, but they went on to study that, and instead, to get rid of the negative, what they did is square. That also gets rid of the negative sign. So if you square all these values, and then you average, that's better. I mean, you'll get a value. You'll get rid of that sign and you'll get a value of the magnitude of deviation from the mean. The average deviation from the mean. but we say the average squared deviation. So I have to square all these values. 6.2 squared is 38.44. 0.2 squared is 0.04. 1.8 squared is 3.24. 7.8 squared is 60.84. And 3.2 squared is 10.24. I don't care about the sign because I'm squaring, the sign disappears. So now I'm going to sum those values, and you can use your stat mode in your calculator or just add them together. 38.44 plus 0.04 plus 3.24 plus 60.84 plus 10.24, and you get 112. So the sum is 112.8. So what we're doing is the tabular calculation of standard deviation. The answer will be this one, but I'm showing you how we get there. So what we did was this. We took the deviation from the mean, we squared them, and we summed them. We did all this work up to here. Whenever you see a number like this in front with an n on the bottom, like here, always call that an average, okay? This is an average. This is also an average, except I have to minus 1. Now, if n is really high, really large, minusing 1 from 10,000, it doesn't do much, right? But n is actually, in this problem, only 5. Why do we minus 1? So I have a whole discussion in my notes about why we minus 1, and it has to do with this. The fact that I am using an estimate inside of an estimate is the problem. And to adjust for the problem or the bias it creates, we need to divide by 1 less. What does that do to the number? It makes the number a little bit larger than it otherwise would be, so that we capture the spread. Like it's just a little bit larger than dividing by n. So it guarantees that we're going to have a good representation of the spread of data. So that's what that's all about. It has to do with degrees of freedom. You're going to read about that in the notes. It's nothing I'm going to test you on, but that's what that's called. That's what that refers to. Because the X bar uses all the values in its calculation, it ties all those random values together. Because there were 5, yeah, by introducing this sample of 5, there's 5 degrees of randomness, but because I connect them all to make this calculation, I lose 1 degree of randomness, and that's why I have to divide by 1 less. Anyways, so that's the formula. We did all of this. We squared, we summed. Now we have to do this. So we're going to divide by, so the sum divided by n minus 1 is equal to 112.8 divided by, well, n was the sample size. So n is the sample size. That's what the symbol for. Big N is the population size. We don't have the population. We have the sample. So n minus 1 is 4. So what is 112.8 divided by 4?
.2.
28.2. All right, so I did all this calculation. Notice, and I have to correct myself here. This is not dollars, right? Because what I've done, I took dollars and I minus dollars. These are all still dollars, but once I square, the units also get squared, not just the number. And dollars squared doesn't make any sense. So we don't say that. What we do is make the calculations, and at the end, to get rid of the dollar square, we take the square root. That's what this is for. Before I do that, though, I want to tell you that this has a special name. Does anybody know what this is called? So this whole inside part has a name. This is called the variance. Okay. And it's the square root, the standard deviation. Oh, let's be more clear. It's the sample variance. The sample standard deviation is actually equal to the square root of the sample variance. Why? Because I need to get back to dollars. The only way I'm going to do that is by taking the square root, and my answer now is in dollars. Otherwise, it was left in dollars squared. So how do I interpret this? This is the mean, this is the standard deviation. What I do is I say, and you can see it in the notes, when I explain this, we conclude that on average, the student has $8.20 to spend, give or take $5.31. So what we can do is say within one standard deviation, the student can spend, or she has, $8.20 plus or minus $5.31. That's what the give or take. Give or take. I wrote give or tax. Give or take. So she can have between $8.20 minus $5.31, which is $2.89 to $13.51. So you add the 531 and you subtract the 531. How many observations are within this range? The $8 is, the $10 is, and the $5 is. So 3 out of 5 of the observations are within one standard deviation of the mean. So it's showing you, it's describing where the majority of the observations are, 3 out of 5. So that's 60%. What about within 2 standard deviations of the mean? Now I'm going to take $8.20 plus or minus 2 times $5.31. So it's 10 minutes to. I'll just make this calculation and I'll leave it with you. For next week, I want you to, like we said, you're going to finish Unit 1 on your own. And you're going to bring me your questions. And then you should have time to start looking at Unit 2 material. But we'll see how far you get. Okay, so finish Unit 1 for next week. I'm going to make this calculation really quickly in my last statement. And you can check your work. So this ends up being $10.62. So I'm going to add and subtract 1062 from 820. This is actually going to be negative, which there are no negatives, but anyway, we're going to just make the calculation. And then so within 2 standard deviations, all the values fall here, okay? So this is actually 5 out of 5 fall in the range, or 100%. So the standard deviation is used in this way to tell you, to describe the spread of the data when the data are symmetric. We have to assume symmetry and we can make these calculations. Do you have to do the table every time? No, I just wanted to illustrate to you this formula so you understand it better. But in fact, the calculator will give them to you right away. So work with the calculator to get the answers. I'm recommending you buy the TIB, the Texas Instrument BA2 Plus. In some of the old videos, I use a different calculator, but in the lectures, I'm always using the TIBA2 Plus. Okay, so there you go. Any questions for me? So you guys have a lot of work to do. Keep me posted on your progress. Your goal is to finish Unit 1 and start Unit 2. The more you can get done of Unit 2, the better. Okay? And then Unit 2 GDS. Then next week, next week we'll talk about Unit 2 GDS, and the following week NOR, and then a review, and then your test. So that's how it's going to be. Right? So keep me posted on your progress and any questions you have. Okay? Good night.
Good night.
Nine.
Thank you.